Hey, so Heather, I'm taking a geometry class this semester, and so far we've learned about Euclidean geometry, which involves flat surfaces. What if it's not a flat surface?
Well, Sam, then it's called non-Euclidean geometry, which includes spheres, hyperbolas, and much more. Why don't we explore spheres and Poincare disks?
Non-Euclidean Geometry by Sam and Heather.
What is Euclidean geometry? Euclidean geometry is the geometry taught in a high school geometry class. It is also known as flat geometry. Euclidean geometry deals with points, lines, and planes, and how they interact to make more complex figures.
What is non-Euclidean geometry? Any geometry that is different from Euclidean geometry. The two most common examples are hyperbolic and elliptic.
Why is it called Euclidean geometry? Euclid was a Greek mathematician who is often referred to as the father of geometry. His book, Elements, is one of the most influential works in the history of mathematics. Euclid's 5 postulates define what we know as Euclidean geometry. Remember, a postulate is an obvious truth that could not be derived from other postulates.
Euclid's first 4 postulates are as follows. The first, one straight line may be drawn from any 2 points. The second is any terminated line may be extended indefinitely. The third is a circle may be drawn with any given center and any given radius. And then the fourth is all right angles are congruent.
Euclid's 5th postulate: for a given line and point there is only one line parallel to the first line passing through that point. This postulate caused great debate between mathematicians and even Euclid himself. It was a very complex statement, and the postulates were meant to be simple. As later discovered, this postulate does not hold for all types of geometry.
Hyperbolic geometry. Exploring the hyperbolic plane using the Poincare disk and Geometer Sketchpad. First postulate, one straight line may be drawn from any 2 points. This is true. In this model, a line through 2 points is defined as the Euclidean arc passing through the points and perpendicular to the circle. The straight lines of the hyperbolic geometry are segments of circles contained in the disk orthogonal to the boundary of the disk, or else diameter of the disk, which is shown below. The second postulate is any terminated straight line may be extended indefinitely. This is true. Since the Poincare disk is infinite, the line segments will also be infinite. The third postulate is that a circle may be drawn with any given center and any given radius. This is also true, as shown to the left. The fourth postulate is that all right angles are congruent. This shows that these two angles are 90 degrees, meaning that they are both equal and right angles. The measurements are shown below. The fifth postulate is for a given line and point, there is only one line parallel to the first line passing through the point. So we start with line AB and point C off of that line. This is actually false. Since there is more than one parallel line, this postulate does not hold true. In a Poincare disk, there can be more than one line segment sharing a point that is parallel to the same line. As you can see to the left, there are multiple lines that pass through point C that will never intersect line AB. In the Poincare disk model of the hyperbolic plane, lines are represented by circular arcs orthogonal to the boundary of the closure of the disk. The parallel lines meet at a common point and do not intersect line AB, illustrating that in the hyperbolic plane there are infinitely many lines parallel to a given line passing through the same point. Poincare disk can be pictured as a bowl. However, the bowl is limited, while the Poincare disk is infinite. To the right, there is a picture of hyperbolic tiling. I thought this was kind of interesting. First, we're going to look at a triangle in the Poincare disk. A triangle, as everyone knows, angles are measured to equal 180 degrees. In a Poincare disk, they are actually less than 180 degrees. So we have the measurements of the 3 angles listed below, and then we also have them added together. As you can see, they do not equal 180 degrees. As we animate this point, you can see how the angles change. As it gets closer and closer, to the line of BC, the angle measurements total will get closer and closer to 180 degrees. So moving point A, we're going to put it close to line BC, and if notice we got 175 degrees. Might get a little closer than that though. We're not sure. Now we're going to look at perpendicular lines. As I mentioned before, lines in a Poincare disk are orthogonal to the outside of the disk. So if you look at angle ABC and angle DEF, they are 90 degrees. As we animate these points to go around, the angle measurements do not change. This proves that the lines in a Poincare disk are orthogonal to the outside of the disk. Now we're going to look at circles. In a Poincare disk, since it is a bowl-shaped figure, the center of the circle does not look as if it is in the actual center. But if you notice, we have AB and BC as the radius. They are equal to each other. So as we animate point B, you can tell that as it goes closer and closer to the center of the Poincare disk, it gets closer and closer to the center of the circle. Notice how the radiuses AB and BC are still equal to each other. This concludes the Poincare disk portion. To continue, go to Ogea Lawson, Non-Euclidean Part 2 to view the spherical aspect of this presentation.